Thank you, Chris. Thank you, Troopers, for having me back. It's cool to be here. I'm Nate Warfield. I am the current Director of Threat Intelligence and Research at Eclipsium, but that's not why you're here. I'll do a little bit about myself because that's what we do. I've been a network engineer. I was a network engineer for about 17 odd years. I've been doing security research against network devices for, 20 something years, if you can call hacking into BBSs as a kid research. I used to work for Microsoft before my current role. I worked in the MSRC, which is the Patch Tuesday team, and was one of the people that helped ship the WannaCry patch. And if it had a logo and a website between 2016 and 2020, it was probably one of the patches I shipped out. I ran the Windows subsection of the MSRC. I also did a little stint at Defender for Endpoints, and I don't know enough about that stuff to really comment. But the fun part is I worked for F5 Networks for 10 years. About 7 of those years, I was Microsoft's dedicated pick up their phone and call my cell phone guy. I helped them deploy somewhere around 2,000 F5 devices inside their internal network before Azure was the big thing. Obviously, I like to speak at conferences. Kaspersky, like I said, I was here at Troopers22 doing a more defensive-focused talk, which I guess I should point out, while you are in the defense track, this is entirely an attack-focused talk. There's like one slide at the end that's going to probably make the defenders sad. This talk is entirely about what you do, trust me, what you do after you hack into an F5, all the ways to not get caught. Please use this information responsibly, and also understand that most of these things that are on the internet have already been hacked. So this is more useful like internal red teams or pen testing. Like this is, I'm actually pretty proud of this one. One of the other things I'm really proud of in my career in 2020, I was one of the founders of a group called CTI League. We basically built a 1,500 person strong volunteer InfoSec group, and our mission was to give healthcare networks and hospitals free perimeter assessments, threat intelligence, basically anything that we could do to help them stop from getting ransomware during the COVID pandemic, and we got written up in Wired Magazine for it. And then in June 2020, the group did sort of open source incident response against the F5 vulnerability I was going to use for this talk, except they blessed me with an even better one in May of this year. And because we're in this kind of cool, I really like this new venue for Troopers, I figured I'd throw out that I used to be a drum and bass DJ, so this type of a scene is very near and dear to my heart. Dark nightclubs and bathrooms and that probably have all sorts of strange substances left on the countertops, so I like this place. All right, so sort of the TLDR on load balancers, if you don't know what these things are, they are just very expensive pieces of networking hardware. It's been a while since I worked for F5. This thing right here seems to be the newest and biggest one they have. Based on what they cost when I worked there, this is probably about a $500,000 to $750,000 piece of networking hardware. And they're deployed in pairs, because if one dies, you want to fail over and be able to load balance your traffic. So think of that when you think of how much money these things cost. Operationally, their failover works very much like HSRP if you're in the routing world. We're going to get somewhat deeper into details just so you understand the architecture, because like I said, most people think of these, and they are, this black box that you spend a ton of money on and it does a thing, but you just get to know it enough to make it work and hopefully not break. So they're designed to do layer 4 to layer 7 load balancing. That's how they've gotten so popular, so anything from just basic TCP up to layer 7 HTTP traffic. F5 has bought over the years a number of other technology companies, and they sort of roll them into their product and put all of the code into one installation image for their firmware. You unlock the different functionality with a license. So they've got a WAF, they've got a VPN device or controller. They have a DNS load balancer, which unfortunately they won't give out demo licenses for, so I can't show you all the evil things you can do when you take over somebody's distributed load balanced DNS system. But if you have an F5 and you have this thing and you want to let me play with it, find me afterwards. SSL and TLS offloading is another one of their big selling points. They got popular in the late 90s, early 2000s when CPU processing was expensive, and you'd buy one of these things, it had an SSL accelerator chip in it. Funny story, their original platforms were literally a desktop computer, flipped sideways, rack mount ears, 2 Intel NICs, and an SSL card. Like, you could actually run Windows on these things if you wanted. And the nice thing about it, and we'll get to this F5 and a block of ice a little later, they generally, because they're networking hardware, they have unfettered access to your network, right? People set these things up. It's designed to load balance server farms, databases, whatever it is. So they're deployed in really important parts of the network, sometimes on the edge, very many times in the core. I can tell you for a fact that probably 80 or 90% of the Fortune 500 in the US runs these things. Every cell carrier in the United States has them. Most banks, US Space Command runs them, Costco, like names you see on the NASDAQ. Sorry, I'm from the US, so we're gonna stick with US terms. I don't know what they call stock exchange in Europe. But yeah, pretty much any big company that has the money has these things because they do serve a purpose at sometimes, especially for people like us. And because they're mission critical and because of questionable code quality from F5, a lot of times when people deploy these things, they don't update them, right? They get them in there, they set it up, they don't touch it. When I worked for Microsoft, we had almost 4,000 of these things that we had to manage, and our code certification process would take anywhere from like 12 to 18 months just to make sure that the build of code that we were going to use wasn't going to take down like Hotmail or Office 365. So that gives you an idea of how people don't want to touch these things. Once they're working, they just sort of leave it alone. So a lot of times you'll find versions that are 5, 6, 10 years old. There was a bank who I won't name. One of the engineers bragged. They're like, check this out. This F5 device is 7 years old. It has a 2,800-day uptime. I'm like, that's not a good thing. And the other nice thing about them, or interesting thing about them, is because they're firmware, they have custom firmware. Their management side runs CentOS, which we're going to get to. But EDR tools don't run here, right? There's nobody that I know of that makes a security solution that supports F5 devices. Not to totally bag on F5, Citrix is in the same boat, A10 Networks, Radware, like all of these application traffic managers are sort of just this nebulous thing that you throw out there and hope that nobody like me hacks into it. So first thing is finding these devices. One of the interesting things that F5s do, and one of their popular features that people use them for, is persistence. This is kind of more popular when servers died a lot. I think these days servers are probably more reliable than they were 20 years ago. But they have this feature that they call cookie persistence. And what they do is you basically build a virtual server, which we'll get to, and you can just say, okay, I want to use cookie persistence on this virtual server. Every web request that goes through it, the F5, as it responds, it'll stick a cookie in there that tells the client, just give this back to us and we'll make sure that you go to the right server when we connect you to the back end. The fun thing about these cookies is you can you can use Shodan to just search for the default name of these cookies. So I just ran it, and there's like 19,000 endpoints that are feeding back this F5 server cookie. And then somebody actually figured out how to build a decoder for Burp Suite that decodes the cookies. And the cookies are essentially the name of it's the big IP server cookie, and then the value is a hash of the backend server IP address and the port that the backend server is using. So you find one of these cookies, like in this screenshot, and you run it through a decoder, you can figure out what the internal addressing scheme is of whatever is behind that IP address. Now, this isn't necessarily going to tell you how to find an F5 management interface that we're going to hack into, but it does give you an idea of okay, somewhere in this general vicinity, there's probably an F5. Let's see if they were dumb enough to leave the management interface on the internet. The other nice thing about people deploying these, like I said, they do SSL and TLS offloading, so a common design, if you're not a bank or somebody who has PCI requirements or whatever the certification is, they'll just SSL the front and then clear text the back. So should you be able to get on one of these things, you can quite possibly sniff unencrypted backend traffic with usernames, passwords, whatever it's talking to the backend server. Could be a gold mine of data if you're trying to prove that you can access somebody's PII that they shouldn't be able to, you shouldn't be able to get to. Sorry, this part's a little bit out of alignment, but they do remote authentication, and say you hack onto one of these things, and you'll notice, just as a sort of disclaimer, You'll see a lot of these TMSH things in quotes. TMSH, which I'll get to, is their proprietary shell. And I developed this talk so that you can use the current POC and you can pretty much paste these commands into the POC and run them against the test endpoint. So it's designed to be, go home and play with this yourself, and it's easy to do. So, getting back to the authentication things, these do remote authentication. They'll do Active Directory, LDAP, Radius, TACACS. The credentials for the server that it's talking to are stored in a config file. I didn't have enough time to figure out how to brute force the Active Directory service account password. They do some sort of salting on their password encryption, but people that are better at password cracking than me could probably figure it out. So it gives you an idea of all of the juicy things that are stored on one of these devices that the admins probably didn't think about. Listing, important part of what we're going to get to, because these devices are deployed in pairs, they have a synchronization mechanism that keeps them in sync. And part of the important part to hacking one of these things, if you decide to go and meddle with their traffic, is making sure that they don't visibly tell you that, or the administrators, that it's out of sync. You're going to see these commands used more beautifully than these slides. But there is a way, if you find one, you can use these list CM device. CM is config management in F5 terms. You can actually ask the device to tell you about all the other F5 devices that it knows about and the other ones that it's talking to. So it's it gives away a lot of information about its friends. If you find one, you may be able to figure out where the other ones are. And finally, the GUI on these things, they have hardware platforms. They also have a virtualized instance now, so you can run them. Most of my lab I built in my house. You can also run them in Azure, so you can use some, I have some Shodan queries that I used to keep updated on GitHub. But if you're searching by looking for the management interface string, which you'll see later, you can filter for 8443 and you'll know that, this is a virtualized F5 versus this is a hardware device. This is important when we get to talking about the capacity on these things. Now, where people get into trouble is management, right? This is how the last two big wide-scale attacks happened to the F5s. So the hardware devices have a dedicated management interface. So it's like a gig port that's not the regular switchboard. You hook it up to a trusted management network, let's hope, and that's great. The problem is that when you set these things up, because it's sort of like an HSRP thing, most people, what they'll do is they'll trunk, however many Ethernet ports into their switch. They're going to put VLANs on these things. They're going to tag them and say, okay, this is, this server farm. This is this database network. This is whatever other thing. You have to assign a non-floating address to each device so that it's statically there, and then a floating address that's sort of the HRP address that's used by those servers as their default gateway when they talk back out. By default, the management interface gets enabled on every single self-IP that the device is configured with. So the 2020 incident, what we saw was a bunch of people saying, hey, I turned my management, my management interface is it's not on the internet, but it's yeah, but your other self-IPs were, and the management interface is enabled on all of those IPs too, and they're just like, what? So yeah, and in general deployment mechanisms, the way F5 says to do this, you'll find, if you find one IP address, search 2 or 3 around it, because people will deploy .1 is my gateway, .2 is this device, .3 is that device. So they usually cluster them very closely. Oops. And then, like I said, behind these things is pools of servers in the resource VLANs. So, like I said, you can discover these with the actual server cookies themselves. You get on the device, you can list the configuration, you can look at the ARP table. They're really a networking device. So there's not a ton that's super unique. If you know Linux networking, once you're on it, you can kind of use a lot of those tools to get around. And this is sort of what these, I'm giving away a little bit of my demo here, but this is what they look like, right? You configure the pool, you put a monitoring instance on it, so you say, okay, is my web server up or down? You have a virtual server that handles all the traffic, and that's how it works. The other cool thing about these things is they have this concept of profiles. So if you think of the OSI model, right, where there's each sort of layer does a certain thing and it hands it up to the layer above it, F5 has designed their devices to be able to manipulate each one of these layers. So for example, these are just port 80 virtual servers. What they'll have is a TCP profile attached, so you can sort of dial the little knobs and settings on how you want TCP to interact. Then you'll have an HTTP profile, which once again lets you dial all the knobs and setting of how HTTP is going to act. If you're doing SSL, you'll have an SSL profile on top of that, which is where your SSL keys and cert configurations are stored, what type of encryption you want to use, like all of the, whether you want to allow like SSL renegotiation, like all of those dials and knobs. So these configuration objects can get very complex if you're looking at it by stealing config files. So it's an interesting thing to know, and there's all sorts of weird ways you can fiddle with things, which is what we're going to do when I demo hacking into it. Actually, which brings me to, they have this cool feature that is their proprietary language that they call iRules. And what it really is it's based off of TCL/TK. You can write a language, this rule thing. You can do anything from inserting cookies. You can send redirects. You can actually, if you really were good at it, you can inject JavaScript into a web page. So you could theoretically put a coin miner in someone's website. If you're good enough with JavaScript, you could put a keylogger into someone's website. The advantage is that this thing is this language is very arcane and most people don't use it, so trying to find out how to do it is very much trial and error. But it's there. This is one of the evil things you can do that people kind of overlook. So a big part of not getting caught is understanding what you can do that'll break these things. They split these things up kind of like most networking devices, where you have a data plane and a control plane. They call TMM is their proprietary load balancing code, is the traffic management microkernel. This is where all the production traffic, this is where all the load balancing logic, all of the stuff that you buy in F5 for happens in TMM. TMM they have a bunch of watchdogs on their devices, so if a network interface goes down or something gets hung, it'll automatically fail over, or sometimes it will reboot. TMM has a watchdog. If you do something that breaks it, the device will fail over, and you will get caught if somebody's paying attention. That's one of the dangerous things with iRules. You can write, if you're not good at coding and you write something that does some weird infinite loop, or you do something that causes it to fail and the process hangs up, it's going to fail over. SNMP traps go out. Like, it makes a lot of noise when it fails over because it's a significant event for a networking device. Now, if you go to the management side, which is primarily CentOS, you can do whatever you want here. They have an interesting way of resource allocation. So what happens when these devices boot up is basically TMM starts first. The device takes all of the CPU and memory, gets allocated to TMM. It then yields back like the user can configure how much a percentage of the resources does it want to yield back to the management side. So it's almost impossible to break the management side to the point where the device fails over. Now, you can lock it up and lock yourself out, or you can possibly get caught if they're watching their MRTG graphs. But you have a lot of freedom once you get on these things. Going back to the hardware thing I was talking about, this command, say you're discovering one in the wild and you want to figure out what this thing is it a VM? You run this shows hardware, it'll tell you the platform details, and the platform details, let's see here, I'll throw this out there and then we're going to talk about the architecture. So the platform is important because if you're going onto a very large device, like I said, they'll connect these things up with multiple 10 gig interfaces. And if you hack into one of these things, like I said, you may want to go and steal traffic from a backend network. Be careful about this. They have what they call a backplane interface that shows up in Linux, which is the entire backplane traffic. Should you start TCP dumping, say this TMM or TMM BP interface, you might be dumping 40 or 80 gigabits of traffic going through the device. This is almost guaranteed to lock it up. They've customized TCP dump so that it hooks to TMM, so it is one of the few things you can do to an F5 that could basically, if you're used to like Cisco, if you like set debug all, that basically makes your switch stop working. So don't do that. Never TCP dump on TMM. This component thing is interesting. I want to kind of give you some history on the architecture. What they did when they switched in the early 2000s from BSD and these basically desktop computers with rack ears on them, they switched to CentOS and they started building their own hardware platform. So they had their own switchboards. They actually had a little embedded secondary Linux system for their always-on management, which we'll get to a very interesting point on that soon. But this stuff in the pink, like I said, this is the traffic plane stuff. This is all the proprietary code. The orange is basically their management stuff. They do have OpenSSL. The devices have Telnet on them. It's not turned on. And they actually can run dynamic routing protocols too. So there's a lot of fun you can have depending on how these things are licensed and set up. The AOM was their always-on management, and they've actually done away with that because it turns out having another little board with another little Linux computer inside a computer that already has a Linux computer wasn't really optimal. In fact, which leads us to the fun stuff. So exploitation. They had these old machines that had this secondary Linux computer. This was their always-on management. And the way it communicated with the main Linux system was through SSH shared keys. So when you first turned this device on, it would go through the installation of the operating system, or the initialization of the OS. And it would connect and it would say, hey, I have a shared key. Let's regenerate our shared keys. Everything is happy. Unfortunately, when they stopped making the devices with this secondary onboard Linux computer, they forgot about this logic in the ISO images of all the old operating systems. So what a researcher figured out was if he downloaded and opened the ISO and pulled out the SSH private key, he could log into any F5 device that was the new model that didn't have the secondary subsystem because the shared key was still there. They just had never ripped the logic out to regenerate it. So this was their first bad vulnerability that F5 had. So you can imagine buying a brand new $90,000 load balancer and all of a sudden somebody's like, I can SSH into that as root. They've had some other vulnerabilities over the years. I believe IOActive found some old Java servlet modules that were in Apache that they were able to get root access through a bunch of much more advanced hackery than we're going to have to do today. 2 years ago, this CVE 2020 came out. And basically, if you remember the Citrix vulnerability, the 2019 19781 path traversal thing that happened right before the pandemic, F5 basically had the same exact bug. I did a talk about this for Okta's conference in 2020, kind of poking fun at the fact that this technique had been disclosed at Black Hat in 2018 by this researcher, Orange Sai. And he basically, this POC, this ... oops, I typoed that, was in his Black Hat talk. And then somebody just basically stuck it into a NetScaler, and they're like, cool, I can get RCE on a NetScaler. And then 6 months later, somebody's like, I can stick this into an F5, and I can get RCE on an F5. We're not going to go super deep into that one, because if you're interested, just Google it. Or NCC Group has an actually really good blog they've kept updated for a year or so, I think, year and a half. The one we are going to talk about is the one that came out in the middle of May. So you'll notice that I have this TMSH. Here's where we're going to start seeing this POC. I'm using this TMSH SOSIS hardware to show me the actual information of one of my virtual edition devices from my hacking box. The really cool thing about this vuln is that unlike the other one, which was basically a JavaScript implementation of their TMSH proprietary shell that literally exists nowhere in their documentation. I worked there for 10 years and I had no idea this thing was there. If you search for this JSP file, it doesn't exist anywhere on their website. I don't know why it was there or who stuck it in. But that POC was really ugly. You had to use curl, and it gave you all this disgusting, not pretty output back. This new one, because it's against the REST API, it's all formatted. So the exploit is not only is it very useful, but it looks good. And like I said, so management, I'm kind of repeating myself here. Now, the GUI is Apache. It's got Tomcat and basically duct tape. Like I said, this stuff is outdated. There's all sorts of weird things that nobody really knows. Like I said, the Java servlet page, nobody knew why it was there. It is a here be dragon sort of place for finding vulnerabilities. And then their API is proprietary. iControl is the one that they first came out with, and then they decided to switch to REST to make the POC look better, I guess. And so we'll get to sort of the guts of this vulnerability. So the way that these things, when you're managing it through the API, you're talking to Apache first, where you're saying Apache to Tomcat, and then this thing talks to what they call MCP, or MCPD is the daemon. It is quite literally a ripoff of Tron, the master control program. Like, that's why they named it MCP. They thought they were clever. This is the curl version of this POC. I'm a big fan of POCs that fit in tweets. I think it's just kind of a very egregious thing for a $6 billion networking company to have a POC that I can fit in a tweet, and I still had room for emojis. You'll also so basically the way this works is it assumes, obviously it needs some level of authentication. Yes, they're using basic HTTP authentication in Apache for this thing. All it needed to begin with was a base64 encoded auth header. Now, you'll notice that's missing in my tweet, because it turns out that the auth header could be literally anything you wanted as long as it started with admin. So if I curl admin at null password, it mostly works, right? The trick about it was they have this F5 authentication token that's supposed to tell MCP, this user has been authenticated. You can now accept commands from them. Problem is, if you stick the auth token, which could be literally anything you wanted, cram the auth token into the connection header, I call it header stomping. I don't know if that's actually a thing, but essentially shoves the authentication token into the connection header, and then MCP's like, cool, you're authenticated. Like, it doesn't care. It didn't matter what the admin password was, if there was anything, didn't matter what the auth token was. You just get this header to go into the connection that Tomcat is making to the internal database, and it's just like, you son of a, I'm in. So, as you might imagine, this caused mass hysteria. The guys, I think the first people that actually built the POC for this was a group called Horizon 3 AI. They were actually pretty cool about it. I'm kind of known for this stuff, so one of their guys reached out to me. He's like, hey, do you know anybody over at Grey Noise? Because we'd like to give Grey Noise the signature of what this attack is going to look like, because we're going to drop the POC on Monday. Yes, got them in contact with it so Grey Noise had a signature ready to go before they dropped the one day. And then after, as I was building this, I asked Grey Noise, I was like, hey, can you tell me all of the mass scanning attacks that you saw? Because this vulnerability made the news, it's now on CISA's known exploited vulnerability list, it was a big deal. So Grey Noise gives me all the payload data, and there was about 1,000-ish payloads in total that they saw being just sprayed indiscriminately across the internet. Of those, 400 and change were basically somebody just running the ID command, which just tells you what user privilege, obviously, am I in Linux, which root, turns out. But this was probably just people testing it. I don't know if Shodan put a test in there, but this is the type of sort of non-invasive way you could test if a device was vulnerable to this CVE. Once after we get to that, there was a bunch of people that were basically running wget commands to download and then run things. These were stuff like Mirai, coin miners, sort of your generic script kiddie stuff. Base64 payloads were pretty popular. I didn't get into decoding all of these web shells to figure out what they are. I'm a data kind of nerd. I like to see what's the prevalence of this type of a web shell from this country. But yeah, about half of them were people just basically echoing a gigantic blob of base64, piping it through base64, and then writing it to the web path to try to give themselves a backdoor. We're going to do something way cooler than some web shell here. But the interesting part that I thought too was, as I started looking through all the authorization headers, it turns out that almost every single person that was spraying this across the internet just used Horizon's POC. They didn't change a single thing. So this wide-scale exploitation was more just kind of miscreants being obnoxious, right? And they were obviously not quiet about it. I'm going to show you how to be quiet about it here in a second. Remaining stealthy. So, anything you do that interrupts the traffic flow on an F5 is probably going to get you noticed. These are, mission critical. People don't like it when they break, so don't do that. Unless you know them like I do, or talk to me, anything you change, just stay away from it, because it's not really that valuable. Unless you want to tamper with web traffic, I'll show you, the real value in hacking one of these things is using it as a pivot point to get into the other juicy parts of the network. Changes that impact the shared configuration, Like the actual device config that's not doing any traffic stuff, like they might get noticed if somebody's paying attention. These things aren't like Juniper. They don't keep a history of configuration changes, so unless you're like downloading them and saving them and diffing them, you may not even notice something changed. And if you change something that's only on a single device, as long as you don't break it, their config management system's not going to alert anybody. So you can fiddle with, base network settings. You can fiddle with their network, sort of their self-allow, which is their sort of ACLing system. The logging, syslog, just basic old syslog. They have SNMP traps. If you configure them, these things aren't designed. They're not set up to be very noisy or very administratable by default. And you can turn off syslog with the exploit. So if you're curious what the syslogging setup is when you're probing one of these, you can list the configuration. It'll tell you if it has remote logging enabled, so you know how stealthy do I really need to be. If they're not remote logging, like go wild, right? The other thing that's interesting, their authentication system, while it's Linux-based, it's sort of PAM-based, they've tweaked it so that you can't create any other Linux users except root. Root's the built-in account, but if you go and try to use add user to add a secondary account, like it'll create it, but you can't actually log in with it. Anything other than root, you have to add through their proprietary system, which is then discoverable, if you will, in the configuration files. And then cleaning up, staying stealthy, history files, they exist, they do them. Whenever you create a user, even through their UI, which is not really a shell account because it won't show up in Etsy password in Shadow, it'll still create a home directory. And so if you log in with that user that you made, just remember to clean out the home, the bash history, and then the TMSH history, which I'm also going to show you how to turn off before you get into the box. Like I said, all of this stuff you could do with an exploit. User accounts. Those are considered shared configuration objects. You might imagine hacking into one of these, or I should say administering, well, just slipped up there. Administering one of these things, you're going to want to have a user account synced. That's if you're using their built-in system. If you're using remote authentication for like against Active Directory, it doesn't matter. Now, you can synchronize these parts of the config without interrupting traffic. It's like, say you make a change to traffic handling and you push it around, there's a chance that it's going to reset. If the change is enough that it needs to reset the way that virtual server is working, it'll drop all the traffic, and so you may have people saying, oh my God, I got lost connection to your website. Like, we're trying to keep people from noticing we're there, right? This is what it looks like when it's in sync. So it'll just say active in sync. If you change something, it detects it within under a second, and it'll say, hey, there's changes pending. Now, will this get you caught? If somebody's staring at it, yes. The thing is the GUIs on these things time out in 5 minutes, so nobody's leaving them open to keep an eye on them. No SOC is watching this stuff. Their advanced shell, hilariously, they call bash the advanced shell. Their proprietary thing is TMSH, like I've said. You can disable the root account through a database variable in their configuration. You can also re-enable the root account using the exploit. Probably not really useful, because if you don't know the root password and you re-enable the root account, you're going to have to change the root password, which once again gives away that you're there. The firewall settings, their sort of firewall list is something that's not shared. So you can basically tweak, if you find out that they've ACLed off one of their self IPs, you can go in and fiddle with that. It's not going to set up an alarm. They don't have IP tables. These things are allowed. Management interface can talk to the internet as much as it wants. Back-end network connectivity, they use sort of like a NAT like you have on your home cable modem, but you have to configure it and say this internal network is allowed to talk to the internet. If you go and fiddle with that, that'll get noticed. There's also the chance you'll break how their traffic is routing, which is bad. And then, like I said, they like to change terms for everything, so they call it the self-allow list when you're in the command line part of the network interface firewall. They call it the port lockdown in the GUI, because why? Once you get on these things, and we're getting to the good stuff, I promise, the /config directory is where they store everything. Your base networking is in this text file, big IP base conf. The formatting kind of looks JSON-ish. The big IP conf is where all of their shared stuff is. So all the good juicy bits are in here, the locations of the SSL certs and keys that are stored on the device, not in an HSM by default unless you pay an extra like $10,000 for that module. The user configuration, or the user accounts. The file doesn't have any hashes in it, but if you go and use the exploit to list it, it'll show you the hashes for whatever that's useful for. And then they have this file store concept. So every SSL virtual you put on there has certs and keys on the device. They store them all in a directory. Just grab the whole thing. You don't need to actually parse the config file. Just steal them all and then look through the config file later. Like I mentioned, I can't show you the DNS stuff, but if they have it, it'll be in this config GTM directory. And then this is back to the F5 in a block of ice. This is me exfiltrating beer. Microsoft had deployed these things in front of Xbox Live like 10-something years ago in the first renditions of Xbox Live going on the internet. And when they finally got to decommission their F5s and switch over to something else, they were so glad to have them out of their network that they put a block of ice around it, ran a beer tap through it, and then had it at a Christmas party. So that's a $400,000 load balancer being demoted to a beer tap. The beer was actually pretty good. So once you're on these things, let me do a quick time check. All right, we're good. So the tools you have at your disposal, because they have this sort of proprietary firmware-ish version of CentOS, they've stripped all the fun stuff out. So you have only Python 2, pip is not installed, you're not going to be able to install any really cool stuff. I'd actually talked to Dirk-Jan, and I was like, hey dude, we should figure out how I can use one of your attack techniques from an F5 to hack into an Active Directory system. And then I realized, oh, I can't actually run Impacket or anything cool because you can't even install the Python 2 version because there's too many missing modules. And you have no build tools. So anything that you want to build, it's CentOS and x86 64. This K article is their knowledge base that will tell you what version of Linux each one of their F5 operating system is running. So you can go and say, okay, I need to know which kernel version to build for. Most of what I'm showing you is all documented on their website. That's the kind of funny part. People think this is like, I'm being my own APT. No, I'm just reading the manual. They have LDAP tools though, right? So I think it's like LDAP, whatever the open source LDAP implementation is there. They've got SMB client because they can talk to SMB things. You've got Netcat. Why you'd leave that on a load balancer, I don't know, because you can use it for a reverse shell. We're gonna show you a better way. And then cron, if you want to do something really noisy and have a cron job that opens a shell, that's fine too. And then, like I said, TCP dump. Now, as I was building this talk, Mandy had came out with this really cool blog post about this threat actor called UNC3524. And while Mandy doesn't specifically call out F5, I kind of felt like they were stealing my thunder from my conference talk because they talk about load balancers being targeted, devices that don't support endpoint detection and response, running older versions of BSD and CentOS. Citrix runs BSD, F5 runs CentOS, you do the math. But this threat actor group had done this very sort of elegant, they built this customized Dropbear SSH client, and it was how they got their backdoor persistence. You know what? Sliver C2 framework that's open source works beautifully, and that's what you're going to see here in just a minute. The etc file system doesn't persist past an upgrade. So trying to drop like an init script into, or an RC script into etc initd is not going to work. If they upgrade the device, that's all going to go away. The user file system, where all these script kiddies were trying to write web shells, is mounted read-only. So some of the more advanced people were sending a remount command, dropping a web shell. I mean, that's great, but if they realize their device is outdated and they upgraded, all of that stuff is going to go away. So how do I achieve persistence? I read the user manual. So they have this thing that they call the UCS file that I kind of blew past, but basically it's just a glorified tar file. And they use this for backups of configurations, and it's copied to new installation locations verbatim. They don't actually analyze the files that are in it to see what they are. It also turns out that on the device it has a configuration file that tells you which files are included in this UCS archive. So I had to go and find and say, which directory can I store my implant in that's going to persist past a reboot and or upgrade? It turns out that /config is the only one I could write the exploit or the payload to. They use, like, they're actually smart enough to chroot named, and most of these other var partitions, like the auto DOS D, I couldn't write to. So I was like, screw it, I'll just put it in config. Like I said, var not writable. But the best part about this is they provide a documented way to run scripts after the device boots up. All you have to do is disguise your payload as some sort of a service so that in a PS list it doesn't look like hacker dot, process or what have you, and then literally follow the vendor documentation to write a script that starts your exploit or your payload after the device boots. And that is going to, update the startup script. And that brings me to the demo. We're going to hope that the cool hacker soundtrack works, and I'm going to try to narrate to you what I'm doing. Fingers crossed. Let's see how this goes. Okay. So I'm just basically showing you devices. Here's my vulnerable guy going to goodguy.com, or my user. This is one active device, standby device. And what I'm going to do here is I'm going to start up a tail on the logging system on the active device so we can show both me getting caught and me not getting caught. This is the showdown query that will tell you this is a management interface, so I know, okay, I'm the attacker, I know that's the place I want to go. By listing this user, I've created a signature for myself. If someone's watching the logs, they just saw somebody do something to the device. So let's turn off syslog. Okay, it even tells me it turned it off, which I thought was really cool. Now, like I said, we know this is a failover pair of devices. We know that this one that we just talked to is the active one. We need to find the peer device so we can go shut the logging off on that thing and also know how to synchronize the configuration across both of them. So running this command tells me the device peer. It also shows me what the IP address of that device peer is. Because I sort of know, you can see .159, I know this is the same sort of network. And this is the configuration sync failover group, right? So I need this information to know where do I synchronize the config to after I make a change. So now I'm going to stop syslog on the peer so that they don't see the logs of the configuration getting synced after I break things. And now we shut off the history logging for TMSH. For time purposes, I don't show you and prove that I did it. You're just going to have to take my word for it. So now we're going to config sync. You'll know those went from changes pending to in sync. So were anybody paying attention, they aren't going to notice that these devices are out of sync. And here's Sliver. Very cool. Play with it. So we throw the actual C2 payload. We immediately get a callback. Now, this is just using Sliver. Okay, it's over MTLS. I use this session. This was actually kind of a demo typo. I thought it was going to tell me the host name, but I was so far into recording it, I didn't want to start over again, so that's not really relevant. What is relevant is uploading the secondary payload. So, come on, Nate. There we go. This is, I guess, what I more went to do. Showing that I'm on the F5 device, this is the list directory. You'll notice all those config files I was telling you about are in here. So I upload my startup script for my C2 payload. That's the startup command from the F5. That's the script that actually starts the payload. Make it executable. Now we're going to start this. I don't know why that's blurred out at the bottom. I'm sorry. We start this secondary payload because if you'll notice on this side, so if I was looking at this device, you'll see this weird bin bash cd command with all this funky stuff that doesn't look right, right? That's going to give me away. So I've started the second payload. I kill the first one. I use the second one. And now you'll see that this basically, if you see, oh, look, there's a bunch of MCPD processes running. Everything is fine. You know, we're all fine here. How are you? I do like this about Sliver. If you go to a shell, it asks if you're an adult before you do it. So now we're in the actual TMSH shell. We're going to start doing bad things. So what I'm doing here is creating one of their iRules to redirect web traffic for our poor innocent user here. And you can see it's fairly simple, right? It's this when request, respond with a free location of a different website. It uses VI, so I hope you know how to use that editor. And then we'll just, showing that the rule is there. You can see that it hasn't actually been used at all. And then for this to be useful, we have to bind this rule to the virtual server that we're going to attack. So I can talk faster than I can copy paste, apparently. We modify the virtual server to put this rule in place. And now, you notice they've gone to changes pending, so we sync it. That way nobody notices what we did. Everything's hunky-dory. And so we're going to kill this session for mostly because I want to be able to get it back to show you that the reboot persistence actually works. So here I am, I'm poor innocent user. I go to refresh my page, going to goodguy.com, and oh my God, I just got redirected to the badguy.com website, right? Completely like transparent to the user, so you could put this into a redirect to a phishing site. Like I said, you could have put JavaScript that inserts a keylogger. Like this is the network appliance version of doing like popping Notepad as system if you follow like exploit competitions. All right, on this side, I just rebooted that device I was on. You'll see that the peer device goes over as active, takes over handling traffic. Because we synced it, the thing is still broken. You know, we've still controlled their website, right? We go to the same site, it still keeps coming back. Now, so here's the device we just rebooted starting back up. One of the reasons you have to use this startup script is that they have this funky way of the networking doesn't come up right away. So if you just tried to put, actually if you try to put something in SE initd, like it'll kind of work, but it'll run it before the networking is started up. Right, so that's actually why they have this solution of like, here's how they have all this script logic to make sure that the networking is up before it actually runs the script or runs your whatever post-boot thing. So we can see it's rebooting, and in a second, you're gonna see my payload come back. Click. So, like I said, reboot safe persistence on this device. Now, because of this thing being stored in their configuration directory that gets packaged up for any sort of an installation or an upgrade, what I couldn't show you is post-upgrade persistence. The VM version of their product doesn't let you install more than one, but when you upgrade the device, what you essentially do is you say, I'm gonna take this patch version, I'm gonna install it to this other boot location, kind of like multi-booting Windows and Linux. It lays down the operating system, it lays down the patch, it creates an archive of everything in the config directory, drops it over there, unpacks it, and then you reboot into it. So you would have thought you were patched, but my implant will still be there after you upgrade. Now, like I said, I don't have a lot of good news for you as defenders. How do you detect this stuff, right? Log files, right? I just showed you turning off logging before I did what I did. So if you're relying on log files, you're not going to see this. In fact, the stopping of syslog doesn't show up in the log file, so you're not even going to notice, hey, why did syslog turn off on my F5 device, and then something weird happened. Devices being out of sync. So, like I said, if you're watching it, which you're not, you're never going to see this happening. So your odds, unless they're being sloppy, unless it's a script kiddie, just looking for these devices being out of sync isn't really a good detection. Configuration changes is probably your best bet to detect somebody doing this, right? So like I mentioned, they don't have a config history system like Juniper does. When I was at Microsoft, they actually they built their own system that went in and cataloged it. Every few hours, it would pull the configs and it would store them in a database. And it was more used for big company configuration management purposes. But if you were to do something like this, assuming that they went in and changed the load balancing config like I did, you would be able to detect that. You're like, oh wow, why did this virtual server all of a sudden have this weird rule attached to it? Or why did somebody do something funky in my device? Now, what I plan to do in the next coming months is build a POC that lets me pivot through the F5 to attack servers on the back end and basically turn it into like a VPN device that I can hack into the back end network. You're not going to find that with a config change. You could find that from weird processes running. But again, this is a Linux box, essentially, when you're looking at the managements or the process list. So tell me a good way. I don't know if anybody has ever said, okay, I can watch every process on my device and I can detect if a weird process shows up. Whether that's feasible, you be the judge. Also, I'm not an APT. Like I said, there's Mandiant's an APT report. I use their documentation in one open source tool that I spent like 20 minutes using to do this. Somebody more advanced than me could probably figure out how to recode the binary so that it shows up looking just like a valid process instead of having a funky, all you have to do is strip that config path out and nobody's really going to know. Newer unrecognized files in your config directory is, at least my version, probably the best way to detect this. They have that configuration file that says what files are stored in the UCS. You can actually modify that and you can add entries and say, oh, I want to also include this file from this weird directory. The problem is that if they upgrade the device, that file gets wiped every time. So it would work for like one-time use upgrade persistence, but after that, it would be gone. But keeping an eye on the files in config would probably help you because, at least to date, that is the only way to keep post-upgrade persistence on an F5. Unknown user accounts, right? If they're sloppy and they create a user account on a device that's not using remote authentication, you can pick up on that. That was actually the first POC that I built, and then I was like, well, I can do better. Obviously, changes in traffic behavior is another way to detect something going sideways. And then changes in CPU load. Like I said, one of the popular things that people were doing, I don't really understand why this is, I mean, I understand why it is, but I don't understand why you'd try to put like a miner on a load balancing device. Like they don't really have that powerful of CPUs. Most of the logic, especially of the hardware F5s, is all pushed down into FPGAs that are at the switchboard. So it's like you could get more Monero by mining on like a hacked Azure instance. But that's another way you could probably, if your CPU load all of a sudden goes from 20 to 50, something probably went sideways and you should probably take a look. So how to do this yourselves? The fun thing is F5 gives away virtual edition VMs for all major hypervisors, and they still give you away vulnerable versions. They don't take old versions off their website. When I built this lab, I was using a version that was vulnerable to the 2020 POC, because that's what I was going to use to show all of you. And then the new one came out, and I was like, cool, 2 for 1. It's also good for testing your compiled toys, right? If you need to go into an engagement and say, okay, will this thing that I built work on this F5? Just build it and then test it in your lab. Like you only need a license to do the load balancing stuff, like I was showing with the shared configuration and the config sync. But if you do need a license, you can get 30-day licenses from F5 for free, and they let you use a throwaway email account to sign up for their website. I think I went through like 30 of them building this talk. Just go to like any throwaway mail, get a free email address, register for an account, ask for some free licenses. They'll send you 30-day licenses. I'm going to find out here in about a week whether I can renew my virtual machines, if I can renew my test licenses with more test licenses, which would seem to be an oversight on their part, but we'll find out. This runs great on Proxmox. This is actually a snapshot of my home lab. This is what I built it on. I say great. It took me about 10 hours or so to get the lab working. There's a lot of weird nuances that you have to be aware of. It also runs in clouds. So I think Azure and AWS both have virtual F5s you can spin up. You can play with them, but you're also going to play for like cloud CPU resource stuff. So just play with it on your house. Like you can use it on Hyper-V at VMware. And you can also download ISO images with the throwaway email. So if your thing is looking through ISOs and finding old libraries and vulnerable modules, like just grab the ISO and unpack it like the dude that found the SSH key. One thing I will warn you, don't buy old devices off of eBay. You can turn them on, they will never work. They changed their licensing model in like 2004. So basically, if you get a device, you can turn it on and it'll say, I don't have a license. You can't just go get a license for a device that works. Like you can buy an old Cisco router, you can turn it on, you can play with it, you can do your Cisco CCNA lab, but just fine. If you call F5, they'll be like, well, you don't have a support contract. And you need to spend a bunch of money on a support contract before we'll give you a license that lets you use that device you just bought off eBay. So don't make that mistake. And finally, if you want to do this and you get stuck, my Twitter handle was at the beginning. I use my full name on Twitter. You could reach out. Happy to help with your research. Again, if you have F5 devices that you will let me play with, I would love to do that, and I will give you shout-outs in my next talk. And like I said, this is some reference material. And I mentioned that, being a DJ in clubs like this is proof. Granted, this is 22 years ago, before I had a beard, and it's also proof that I wasn't born with this beard. But yeah, so I hope you all enjoyed this as much as I enjoyed giving it to you. I think we have 5 minutes for questions, and if not, find me. I'll be here until Saturday.
So, thank you very much, Nate. What shall I say? Awesome presentation. Thank you for your contribution. Expectation exceeded. This is what Troopers is all about.
Too kind.
So, any questions? There is one.
Yeah, great stuff, man. I mean, it's maybe an open question, but do you know the call out, if you go to the C2, from which interface that comes?
It'll come out of the management interface by default.
Right.
Yeah, so they do separate their management interface and their traffic interfaces. I am going to figure out how to make it call out of the traffic interface, but for this lab, because of the way my Proxmox lab is set up, the virtual server you saw me hitting can't talk to the internet. But yes, I'm working on that.
Yeah, because probably it shouldn't be on the internet in the first place, right? But if you pick it up internally, probably the outbound interface is also blocked for the management interface. So if you have a way to route it internally from a normal interface, that would be preferred.
Yeah, like I said, I just got this POC ranking like last week, but yeah, getting it to do exactly that is on my to-do list, so stay tuned.
Hi, thanks for the talk. You said there's cron running on the machine. Would it be possible to use this for persistency, to use this at reboot functionality from cron?
For cron? Yeah, actually, the first POC or the demo that I was going to do was building using the @reboot command in cron to basically establish C2 out. And yes, you could do exactly that. You could just say @reboot, do this thing. I just thought it was more fun to abuse the functionality that they spent time developing to do this.
Any more questions?
So on you had a list of the things that could be done to prevent this. Obviously, proper patch management was missing there, because if the box would have been fixed, I think your attack wouldn't work, right?
Oh yeah, absolutely. I kind of inferred that proper patch, I work for the Patch Tuesday team, so me saying patch your stuff is kind of redundant. But yes, if you keep these things updated in time, of course it's going to stop it. My point is that because of these things being so mission critical, and because a lot of people will say, oh, if I saw this CVE, they're like, hey, your manager says, hey, are these things internet exposed? No, they're not internet exposed. Okay, cool, don't patch it. We don't want to worry taking down the network. So more useful for an internal red teamer or a pen tester, but just wait a year or 6 months or so, and there'll probably be another F5 RCE that's on the internet that you could do the same thing with.
So, one last question.
If you execute the code of the exploits, would it be a difference if you have a cluster of 2 machines?
If you execute the code, it doesn't really matter if there's a cluster or not. Really what you're targeting is just a single machine. I was trying to actually get a POC where I used the Python POC to then pass the curl POC to hack a machine that wasn't exposed. I got frustrated and couldn't figure it out. But no, the clustering doesn't really matter. And in fact, the clustering now, you can have like 3 or 4 or 5 devices in a cluster. So theoretically, you could discover all of them and then try attacking all of them. It's just kind of how bad do you want to get.
All right, then again, thank you very much, Nate. So he will be here.
Thank you.